Yes, thank you, Mr. Chairman, and good morning. The title of my talk is Low-Actuation Voltage Design for RF-MEMS Switch. As my title suggests, this talk will describe the novel low-actuation voltage design targeted for RF-MEMS switch application. I am Horng-Hsiang and from National Tsinghua University, Taiwan. And the first order Horng-Hsiang Lai has graduated and was not able to come, so I will present his work here, and all the credit should go to Horng-Hsiang Lai. Thank you. To give a brief outline, I will start with major motivation behind this work with a circuit and MEMS integration, and to realize a low-actuation voltage design switch, I will introduce the working principle of the switch structure used in this work, followed by theoretical and finite element simulation. And I'll then implement such a switch via CMOS-MEMS technologies. To emphasize, such a process is from a generalized platform. I will demonstrate a variety of flexible design options using CMOS-MEMS process, and I will show you the fabrication results. And I'll then present the experimental results for device characterization. And finally, I will conclude this work. And nowadays, as we can see in the pictures, there are many applications which can be implemented by RF-MEMS switch. First, mass application, including mobile phones and consumer electronics. Second, high-value application such as satellites and military application. And third, the microwave communication. And last, the application of automotive and RF instrumentation. And we can define RF-MEMS switch into two categories by contact configuration, which are DC contact switch and capacitive switch. And we can see the example of the Raiden MEMS contact switch and Wen-Chien MEMS capacitive switch. On the other hand, in terms of the actuation mechanism, there are three major types, which are electrostatic actuation, such as Rockwell switch, and magnetic actuation, as microwave switch, and thermal actuation, as UC Davis DC contact switch. Among them, the switch using electrostatic actuation facilitates the integration of MEMS and circuits, therefore advantageous to low cost and small form factor, less parasitics, and faster turnaround time, especially for consumer and portable electronics. Therefore, in this study, we are focusing on the contact switch of the electrostatic actuation for the extended frequency range. And here I will introduce the switch design and show you the simulation results. First, I will introduce the switch structure proposed in this work. And the pictures present the perspective view of the CMOS-MEMS switch structure. Employing a pulling ADD frame is my key design. And the actuator structure here is suspended on the top of the coplanar waveguide and through its external supporting beams. And the driving electrode and the inner stoppers are beneath the structure via a symmetrical design approach. And let's see some draining fields and cross-section fields. Here is the draining of the central contact region, and we can see the contact tip here is used for passing the signal. And its AA cross-section view shows the profile of the major pulling frame. And its BB cross-section view shows the pulling ADD frame. And its CC cross-section view shows the profile of total structure with GSG coplanar waveguide, which is a ground signal RF signal lines. And its operation mechanism. When the DC bias voltage is equals to 0, the switch is open. And when we apply the voltage to the VP measure, then the pulling of the major pulling frame will occur, and the switch is short. And then we raise the voltage to VP added, which is larger than the VP measure. Then the pulling of the pulling added frame will occur for deep contact. With the higher DC bias voltage, we get a larger contact force and lower resistance. So we can improve the insertion loss by this way. And here shows the simulated actuation performance of the conventional single-stage design and the proposed two-stage design as the DC bias voltage increases. And we can see when we raise the voltage to 27 volts, the displacement of the single-stage actuator is only 0.12 micrometer. And since the two-stage design achieves a 0.48 micrometer displacement, which is 4 times larger than the single stage. Until the 45 volts, the single stage achieves a similar displacement as the two-stage design at 27 volts. It clearly shows that with pulling additive frame, we can effectively lower the pulling voltage by 40%. And we know that the switching time is inverse to the fundamental frequency as shown in the formula. So here shows the resonance frequency simulation by console, and the frequency of fundamental mode of the switch structure decreases from 82 kHz to 72 kHz. It's just a little bit change. So we can indicate that the switching time doesn't affect much. And then I'll show you the fabrication process of the CMOS-MEMS switch. A generalized CMOS-MEMS platform developed for the CMOS-MEMS resonators was now adopted for switch fabrication. To fabricate the switch, the chips were manufactured utilizing the standard 0.352P4N CMOS surface from TSMC with a cross-section view as shown. And 2P4N means the two polysilicon layers, and 4M means the 4 metal layers, which is aluminum. And the post-process in this work is very easy. A silicon oxide etchant with a very high selectivity to metals, vias, and contact is utilized to release the switch structure. And the circuit is protected by the pacification layer. And after wet release process, the switch structure is realized by this platform. And let's see some SEM views. It's the overall views of the chip. And we can see some drain in each part. Here is the left side of the chip. It shows the major pulling frame and the pulling added frame. And it's the drain in of the pulling added frame. And we can see the air gap, stopper, and driving electrode. And here is the drain of the major pulling frame. And we can see the air gap, driving electrode, and inner stop here. And here shows the drain in of the central region. And we can see the air gap, contact tip, inner stopper, and the GSG coplanar waveguide. So then I'll show the experimental results for device characterization. Here is the here shows the 3D profile of the fabricated CMOS-MEMS switch structure, and we can see its movement with its animation. Oh. Some problem. Yes, we can see the animation. And then to investigate the switch structure after released, The central region was measured by optical profiler with radius of curvature of -11 mm, indicating the existing residual stress of the constituent CMOS layer has less effect thanks to symmetrical stacking layer. And here shows the measured actuation performance of the switch structure, and we can see the pulling voltage of the major pulling frame is 25 volts, which is similar to our simulation results, verifying our low-actuation voltage design. And here shows the frequency, resonance frequency. And the frequency of the switch structure is measured by laser Doppler vibrometer. And the frequency of the fundamental mode of the switch structure is 75 kHz, in good agreement with our simulation. So we can indicate the switching time doesn't affect due to the pulling added frame much. And I will conclude this work. First, with a two-stage mechanical supporting design, the pulling voltage has been reduced by 40%, and the pulling voltage of the major pulling frame is 24 volts, which means the low-actuation voltage design is achieved. And the measured fundamental mode resonance frequency is 75 kHz, shows there is no significant degradation on switching speed in this work. However, unfortunately, the insertion loss in downstate here has 23 dB. Ideally, it should be near 0 dB since the switch is short. The problem here is because of the oxidation of aluminum on the metal surface. So, in the future work, we will try other metals from CMOS-MEMS process, such as tungsten, to generate direct metal contact, or use electroplating techniques to have the contact metal. And since the CMOS-MEMS platform is an integration of the MEMS and circuits, we plan to realize various RF building blocks on one chip for wireless application in the future. So thanks for your attention.